Um, so thanks everyone for giving me this opportunity to talk today. Sorry I couldn't be in there in person. As Peter said, a number of us are at a meeting in Madison, Wisconsin, actually. So I'm sure there's a few of you in the room that might even be from Madison. So, but it's a great polar conference and all of us sea ice folks are there, including Alice Duvivier and Marika Holland. So this is a group of my collaborators that have contributed to this presentation over the years. And in particular, I want to especially call out Alice Duvivier, who has given this presentation over the last several years virtually. And so it's really nice that you can be there in person. So, and hopefully we'll get a chance to talk to you sometime in the future. So sea ice in the CESM. Well, what is sea ice? So what we're talking about is frozen seawater. And so it forms in both the Arctic Ocean and then in the Southern Ocean around Antarctica. It's comprised of a lot of different flows. You can sort of see here in this picture, there's a lot of different sizes of flows and things like that. And then it also has interesting characteristics where over the summer months, you actually get these melt ponds that form on top of it. So these blue areas in this upper right picture here. So it's very exciting. And I mean, these are from the NASA Operation Icebridge campaign where they took photos from an airplane above. But what we're trying to do is we're actually trying to model it. And I will highlight too that it's different from land ice, which is compacted snow that grows over time on land and can actually break off into icebergs. But that is, can sometimes get confused with sea ice, which actually forms from the ocean itself. So it forms in the ocean and it melts in the ocean. And so it doesn't actually contribute a net sea rise impact globally. But what it can do is do a regional thing where it takes ocean water, freezes it in one part of the Arctic and then moves it around and melts it, say, in the North Atlantic. So so it can definitely move that mass around, but it doesn't actually, add or take away net mass in that case. So to give you some ideas, some scales, this photo here on the left is someone standing on the edge of what's called a lead that was kind of refrozen. And then you also see all this crumpled up ice, which we refer to as a ridge. And so there's lots of mechanical deformation and things going on with this. And then in the middle photo here, you can see these leads, which are actually like cracks in the ice where you can see the open ocean underneath. And then this photo on the far right is actually comprised of a lot of different things going on here. So you see these light blue, green sort of melt ponds on top. You see these white snow covered areas. You can even see like some ridged, really interesting deformed parts. And then these very, very dark patches are actually open ocean. And so that's going to be on my next slide, but I'm going to talk about albedo differences and why the open ocean versus the sea ice is really important. So, but first, I guess I'll motivate it by showing you some differences between the hemispheres. And I wish this was more of a Q&A because I would love to throw this out here and let you sort of tell me what differences you see. But instead, I guess I'll just tell you straight up. But the one thing to notice first is that the Arctic Ocean is an ocean bounded by land almost all the way around, whereas the Southern Ocean is ocean surrounding a big continent, a big ice mountain. And so what that means is that in the winter months, you can see here in the Arctic that when the ice expands, it eventually hits land and it can't really go much further. Now, there are areas like the Labrador Sea, over here in the Greenland Sea, and over here on the Pacific side in the Bering Sea, but it can expand a little bit there. But in the Southern Ocean, there's no boundary all the way around. So it could just keep going towards the equator. But what stops it is the warm ocean. Eventually, the sea ice gets far enough north that it just starts to melt and that it can't sustain an ice cover there. So that's the one thing I want to notice. I want you to notice. But then another thing is, if you look at these numbers down at the bottom, hopefully you can see this, but the minimum extent in the Arctic is somewhere about 5 million square kilometers, and its maximum extent is just under 15 million square kilometers. Whereas in the Southern Ocean, the maximum extent is more like 18 million square kilometers. And in the Southern Hemisphere, it's under 3 million square kilometers. So the seasonality is very different. There's a huge seasonal cycle in the Southern Ocean, where the ice melts back almost all the way to the continent around Antarctica. And then the other important thing I wanted you to sort of take away from this is not just the sort of seasonality and the boundedness and things like that, is just sort of you'll notice here, this is September minimum in the Arctic, but that's actually about the maximum in the Southern Hemisphere. And again, I would throw it back to you as a question, but the hemispheres have different solar cycles. And so the min and max are opposite seasons. And so you always have to keep that in mind when you're thinking about this. And so when we build a model, we have to take all of this into account, that we have both hemispheres that we're including in a global model, and they're very different in their sort of sea ice characteristics. And another thing that maybe you've sort of seen in the news, maybe not, is if you look at and you just sort of count up the area in the hemispheres, there's this total area of just where there is ice. You'll notice here that over the satellite period in the Arctic, the lower panel, since 1980, when we started having satellites, we've seen a significant decline in the total ice area in the Arctic. Whereas in the Southern Hemisphere, what we actually see is that it's kind of flat, and actually arguably there's sort of a slight positive trend in the Southern Hemisphere in terms of its ice area. That is at least until about 2016. Then something really interesting happened in the Southern Hemisphere, where we've seen these anomalously low years in terms of the ice extent in the Antarctic. And there's actually a lot of presentations at this meeting that I'm at that are talking about this and what sort of things have happened and what seems to have happened over the last couple of years. There have been these anomalous ocean currents that have brought in warm water from higher or sort of more equatorward waters, and it's warmer, and that seems to have created this anomaly. Now, it's outside of this sort of gray spread, which is the sort of variability metrics, the one standard deviation of the average sort of thing. But at the same time, it may still be within that sort of internal variability within the system. Anyway, so I talked a bit about albedo on the other slide. So there's a lot of interesting things going on with shortwave and longwave fluxes and so forth in the polar regions, where you have this incoming shortwave from the sun, and then over the ice sheets and over the sea ice, it's a very bright surface in general. So if it was just snow covered, then the majority of that is actually going to be reflected right back to space. Clouds, as you probably heard about earlier this week, also tend to reflect most of that shortwave radiation back to space. But then the other thing that goes on is that there is still, even from the open ocean and the sea ice covered areas, you still have some of the infrared, the long wave, being emitted and going outward, and it could be trapped by clouds and sent back down, or maybe it could just be captured by a water vapor in the atmosphere and then sent back down towards the surface too. So it creates a lot of interesting radiative loops going on here. So that's a really key part of it. Here's another neat slide to look at. And so what you can see here is generally the open ocean areas, the dark areas, have an albedo of about 0.1. So what that means is only 10% of the sun's radiation is reflected back to space in the open ocean areas. Whereas over the sea ice, especially snow-covered sea ice, it's more like 80% of that radiation that gets sort of sent back to space. And you can see over the land areas, the albedo does tend to vary depending on the type of surface you're talking about. But in the snow-covered regions over land and over the ice and the Greenland ice sheet, then you do get really a lot of shortwave reflected back to space as well. So what this is it creates sort of this interesting feedback loop, which we refer to as the surface albedo feedback. And there's many aspects of this, but one of the main things is that as the surface is warming, due to global warming, that this is a positive feedback that makes the ice and snow melt, and it reduces the amount of ice that's there, especially the sea ice. And so what you're actually finding then is that all of that leads to a lower albedo in general, because you're opening up more of this dark ocean and you're absorbing more in the system. And then that's all influencing the surface albedo, which then feeds back into the surface temperature warming again. So it's this difficult thing, because what we're seeing is a manifestation of global warming at the high latitudes, where due to this surface albedo feedback, it's a much stronger amplification of the warming at high latitudes. There's also the sort of freshwater and salt part of this, which is kind of interesting too. So in the central Arctic here, we're generally growing ice and not melting too much. And so when we grow ice, you actually dump salt and you dump water back into the ocean when you grow it. It does trap some of the salt internally, but in general, you're sort of having this salt rejection. And then what happens is, as the ice is sort of transported around here, it goes out into the North Atlantic primarily, so the Labrador Sea, the Greenland, Denmark seas, and this is where it all is melting. And so you're getting fresh water put back into the ocean in the lower latitudes. And this is sort of an extended idea of the global overturning circulation. You're familiar with it here, sort of in the Labrador Sea, where you're getting deep convection. You've got warm, salty water moving northward, coming into the Lab Sea. You've got cold, fresh water coming from the north. And this creates this, perfect storm situation where you can get deep convection overturning in the Labrador Sea. But it does extend up further into the Arctic. This warm, salty water actually makes its way all the way up into the Arctic, and it kind of dives down fairly deeply. And there's this layer underneath, like at about 1,000 meters or so. But at the same time, you've got this relatively fresh sea ice that's moving around and coming out of here, and it's a net freshening to this system. So again, this is another way that potentially changes in the Arctic ice cover could have an impact on the global ocean circulation. So what are the key points to this? How do we do this? How do we try to model this, difficult, disparate set of flows? Well, we have to kind of have some sort of continuum approximation to this. And ideally what we want is a model that will reasonably simulate the sort of mean state and variability of the sea ice. So those earlier trends that I talked about, that's something that we're really looking for in the model. That's a metric that we use to evaluate the model. It needs to also realistically simulate the ice ocean exchanges between the atmosphere and the ocean. So heat, water, salt even. And then what we want to do is these feedback loops, like the ice albedo feedback, we want to make sure that in response to these climate perturbations, that the model is operating appropriately and will give you about the right sort of impact that we see in reality. So the two primary components, and I'm trying to sort of be cognizant of the time here, so I might zip through some of this, but there's two primary components to building a sea ice model. We have a dynamic formulation, and I'll show you the equation on the next page. And then we also have a vertical thermodynamic formulation too. And this solves for the internal ice temperature profile and also takes into account some vertical and lateral growth and melt processes. So the dynamics, solves this force balance. So, and I'll talk about that a little bit, but basically what you have is the wind blowing on top of the sea ice, and you have the ocean sort of dragging underneath. There's a fundamental force balance there that happens, resulting in ultimately the way that the sea ice tends to move in an average sense, or even on a day-to-day sense, and then the thermodynamics, then you're thinking about the vertical temperature profiles and the vertical lateral melt growth rates. But then the other thing that we also need to add too is, because we don't explicitly resolve a lot of this at 1 degree resolution, say, we have to have some sort of probability density function, or PDF, of the ice types that are within a grid cell. And this is just done in sort of a statistical sense, but then this PDF is advected around with the main ice flow as well. So currently CSM2 is using CEIS version 5.1.2. This has traditionally been known as the Los Alamos sea ice model. And in CSM3, we'll be moving to a newer version of the Los Alamos sea ice model. But now this is developed and maintained via a CEIS consortium, and many institutions and groups internationally are all collaborating together to help forward the development of this new model. And so it'll be a CEIS version 6, basically coming in CSM3. So then let me just first talk about the dynamics a little bit. So don't focus too much on this big equation. I think of this generally as sort of an F equals ma sort of relationship, where this is the acceleration, the du dt times mass, and all of this on the right is the F, the forcing part of this, right? And so what we have is we have a Coriolis term, which means that there's this tendency to move to the right in the northern hemisphere and to the left in the southern hemisphere when you have things in motion, and it's due to the rotation of the Earth. You have air stresses, you have wind blowing on top of the sea ice, and then you have ocean stress from below, where it's dragging on the sea ice generally. The other thing we have to take into account too is the fact that there are waves, there are big sort of height gradients in the ocean too. And there's a tendency for the sea ice to sort of slip down these from higher points to lower points too. And so we actually take that into account in the dynamical equation as well. And then this final term is an internal stress term. This represents the sort of crashing of the ice flows and the stresses and the strain between each of the individual ice flows. And it sort of follows this original Hibbler formulation back in the 70s and the 80s. He was sort of the godfather of sea ice models. And I will say that if you're having trouble sleeping in Boulder right now, I encourage you to pick up this manuscript. It'll definitely help with that issue. So the force balance, as I talked about, in the Arctic, it's, largely the air stress. That tends to be the biggest term. And then that's just because the winds are so strong in the Arctic. That's what provides most of the force on the ice surface. This is counteracted somewhat by the drag from the ocean underneath. But then you see in this curve, there's this internal ice stress term, this green curve here. Hopefully you can see it, but that's that last term that I talked about. That's the stress strain relationship. And it is relatively small by comparison to these other two terms, but it is certainly very important in certain regions, like especially near land, when you're getting a lot of drag and other things happening near the land. And especially as the ice gets thicker, it tends to interact a lot more and cause other flows to slow down and so forth. So in the Southern Hemisphere, though, it's almost all explained by this balance between the air stress and the ocean stress. And that is because, again, it's unbounded, right? It can just sort of go and go and go. And there's not much internal stress going on internally in that sea ice. And it's a regime that we often refer to as a free drift simulation. So again, just some more details about the air ice stress formulation that we use and some ocean ice stress formulation. Happy to chat with you some other time about this. And then again, we are conserving all of this when we're doing this. And so as ice touches land or other ice flows touch other ice flows, then again, we're relating this to this stress strain relationship internally in the sea ice that was formulated by Bill Hibbeler originally. We actually use this slightly modified version of it. It's called an elastic viscous plastic formulation. That means that we add a small amount of elasticity in the sea ice, and that allows us to solve the equations explicitly instead of implicitly. So it's essentially a numerical trick to make it a faster solver and so forth. But there are some slight consequences with this, which I won't get into here. So now thermodynamics. So this picture is great. I had originally found this on the web somewhere, but you can see here this really thick ice over here in the upper right part of the picture where it's really dark underneath. So there's very little light that's penetrating through this ice. And yet in other areas, you can see it's a lot brighter, a lot lighter blue. And that's because the ice is much thinner and you can actually get a lot more shortwave penetration. And it tends to be the sort of blue elements that, or the blue part of the spectrum that can get through to the ocean. And this is really important for biology, which again, is a whole other thing. You can get these blooms underneath these relatively thin ice areas. So the thermodynamics is essentially a 1D conduction equation where we solve for the internal temperature as a function of the net shortwave that gets in and how far that net shortwave gets down into the ice and through the snow sometimes. And then there's also heat available from the ocean too. And so we're solving an energy balance at the bottom where the heat available from the ocean is sort of balanced by the conductive flux away from the bottom. And then similarly at the top, there's a net conductive flux into sort of the surface layer. And this is balanced roughly with the absorbed shortwave amount, so the 1 minus alpha times the incoming shortwave. The long wave part of this, there's a net long wave heating at the surface. And then again, you have sensible and latent heat fluxes that are happening along with this. The internal structure of the sea ice is very complicated too. You have all these like micro pockets of brine and water and even algae and all sorts of things going on in here. So it's a very complicated thing. So this vertical heat transfer equation that we're using sort of just solves this in a bulk sense. We can't really do all of the details that you see in this microscope picture of sea ice, but we try to represent a lot of these processes in a bulk sense in a grid cell. Another important aspect that I've mentioned a number of times is the albedo, and in particularly the albedo feedback. And you can see here during the winter months, I mean, there's not really any light back here, but then as you start to get into more and more light coming in, the snow is relatively dry. And so the albedo is very, very high. It's like around 0.8. But then you can see as you start to get water in the snow and these little melt ponds forming, that it can really drop significantly. In fact, even into the summer months when the ponds are at their peak, you can get down to like a 0.4 albedo. So you can imagine the difference between the reflection of shortwave in this white area versus these little ponded areas. And then in the fall, what happens is the ice starts to come back again, you get more snow accumulation, and then the albedo starts to come up again significantly. And we do solve for this internally in the model. We have this complicated Delta Eddington shortwave radiation scheme, and it's been around for quite a while now, but it also takes into account potential pollutants that are going on. So black carbon or dust or other things that could be landing on top of the ice and the snow. And so this is a complicated one-dimensional radiative transfer model that takes all this into account. So, you know, we've developed a pond parameterization to sort of represent these things statistically, again, in a grid cell. So it's sort of an average depth and an average fraction of ponds. And you can see here that with and without ponds, there's a significant change in the surface energy budget over the sea ice. You know, in a one-time CO2 or an 1850 sort of simulation, this is up to 4 to 5 watts per meter squared difference with and without ponds. And in a 2-time CO2, so maybe a future warming experiment, and we're almost getting there, you can see it's up to 10 watts per meter squared of an impact on the surface. And it's that darkening of the ponds that can really drop the albedo that's key to this. And then similarly, you know, we think about aerosols like dust and black carbon. This is generally a smaller effect. You know, we've looked at this and you can see at most, even in a one-time, 2-time CO2 climate, I wonder, these actually might be reversed. Actually, I don't think they are anyway, but basically this is, you know, an order of magnitude smaller. So like 0.8 watts per meter squared difference due to this. So the ice thickness distribution, I don't want to spend a huge amount of time on this, but basically this is trying to sort of represent all of this different ice that's going on in this picture, you know, and you can see here that these are sort of a path looking at the ice from below and above. And you can see there's lots of ridges going on. There's big growth going on in some areas. And so, you know, it's an amazing conglomeration of a lot of different ice types and everything going on. But again, we're going to represent this in sort of a statistical PDF sense. And so what we do is we break it down into these thickness categories, and we solve these energy budget pictures in the thermodynamics over each of these individual ice types. And so, you know, the largest portion of the ice is below the water. But, you know, there's snow on top of here. There could be ponds, there could be aerosols in each of these individual ice categories. And so it can be a complex thing. And what we're doing is we're actually advecting this around with the ice throughout the model simulation. So this is just sort of the mathematics of it, you know, so you can imagine if you started out with sort of a distribution of ice that looked like this, where it was sort of a 2-peak situation, where it was 1 meter-ish first year ice, and then maybe some 3 meter-ish multi-year ice. And then what happens with the PDF is as you advect it, then you see that during deformation and things like that, you could imagine this shift from the green to the purple area where you're gaining ice, but you're actually losing a bunch of this thin ice and losing open water area. So yeah. And then similarly, you can just through thermodynamic growth, you're going to lose open water because you're growing a bunch of ice, and then you're already accumulating onto the rest of the ice categories. So the basic summary I think I wanted to get to here, because I do have some science things I wanted to talk about a little bit, but right now we have this ice 5.1.2 and CSM2 has this EVP dynamics, this sophisticated mushy layer thermodynamic scheme, which I didn't get into too much, but we've got 8 sea ice vertical levels and 3 snow vertical levels. We've got the subgrid scale ice thickness distribution with 5 categories in it. So these are all based on the different thickness types of the ice. We've got an ice melt pun formulation, and then some details about how we compute the freezing point underneath the ice when we're coupling with the ocean. We're currently trying to develop more in terms of the biogeochemistry. We've got water isotopes in there, but there's some, maybe you'll hear about it, but I think that there's been some issues with the isotopes and we're not quite there yet in the fully coupled system, but it's there in the ice. But we're going to have a new way to represent all those individual flows that you saw on some of the earlier pictures. Some more sophisticated snow physics to account for blowing snow and other things. But the other interesting aspect that we're looking a lot at is better ways to compare to observations or incorporate observations into the sea ice. And one way to do this is you use a satellite simulator where you actually output from the model a quantity that a satellite sees, say. So I'm going to show you some science highlights here, just basically some of the recent results from CSM2 versus CSM1 and so forth. These were the runs that we did for the CMIP process. And you can see here that the NSIDC is in blue, this curve, and then the sort of red curve is a suite of the simulations that were done with the high top version of the atmosphere model. And actually, we're capturing the general trend of the NSIDC quite well in terms of the area. This is a subtlety of a model, is that you have this internal variability and you're not necessarily going to get these sort of year-to-year wiggles, the variability that goes on here in the model. And you can see this sort of ensemble that we have. This is just the low top model. We do have a bias here. We know that it's too low, but you can see some of the individual ensemble members sort of get up closer to the observation. And again, this is just sort of saying in terms of the climatology that the seasonality of this, we see that the NSIDC has a much larger or slightly larger extent maybe than we're getting in the model during the winter months. And then you can see we're actually overestimating the area in the summer months. And so these are interesting questions that prompt ways that we can improve things. And again, back to bringing in observations to inform the models to try to improve the representation of some of these things. Similarly, we can look at other satellite observations like ICESat, for example. The ICESat-1 was up in the early 2000s. We haven't actually started looking at ICESat-2 results yet. But again, you can do very sort of qualitative assessments here and see that we're a bit thin, generally compared to this. But also, there's, again, this variability in the model too that could partly explain some of this. I did some separate experiments myself where we evaluated the original thermodynamics against the new thermodynamics. And you can see that sometimes these changes internally in the model really change the overall thickness of the experiments. And this mushy layer, which is much thicker, the blue curve up here, that it includes a much more sophisticated parameterization of uptake of water and salt when it freezes. It actually has a much better representation of when the snow goes below the sea surface, and then we'll get flooded, and then you'll actually get changes from snow to sea ice. And so you can see that. But in terms of the southern hemisphere, it actually, the change in thermodynamics really doesn't change things that much. And that's because again, fundamentally, as I said earlier, the southern hemisphere has really different sea ice and different characteristics. So finally, this is some recent work by Patricia De Repentigny, who's also here at this meeting. But she's sort of showing that there are, like many modeling centers from around the world are running these simulations. And I think the year changes, and there are some biases, of course, spread across the model. I think the key way from slide is where they end up about 20. I think this is looking at a sort of a business as usual scenario into the future. And basically, we're going to be by 2070 in an ice-free Arctic Ocean. Now, this is September, so this is only at the minimum, but we could definitely see this change happening. So this is March sea ice extent, and you can see that even in March, we're getting quite a significant drop in the trends in those months as well. So, so overall, if we don't do anything with the current climate, we know that the summer sea ice in the Arctic is basically going to go away. And we're going to get into a regime that maybe looks more like the Antarctic. And then similarly in the Antarctic, I talked about this initially, but the trends in the Antarctic are actually slightly positive. And this is before the big recent drops and so forth. And so this is actually a bit of a problem in the model, that we can't really capture this flat or slightly increasing trend in the model. It wants to respond to global warming, and it really wants the ice to go away in the southern hemisphere. And this is common across all the CMIP models, that we can't really find this. And it's because essentially that there are missing processes within the sea ice in the southern hemisphere that are leading to this sort of problematic simulation of the southern hemisphere. You can also see here too that the seasonal cycle in the southern hemisphere, it gets higher, but then look at the drop off that happens like in November, December. And again, we're not capturing that quite as well. It's much slower until like February, and then all of a sudden we're caught up again. So there's some interesting aspects of the seasonality that may also be related to the long time temporal changes. So I am running out of time, but with that, I will leave it. And hopefully there's time for a little bit of questions. So with that, thanks.
Here in the room, can you hear us okay?
I can hear you. You might have to repeat questions for me.
We have people on mics, so hopefully.
Okay, great.
So I'll hand over to the mic now.
Hello, could you hear me?
Yes, I can.
Okay, thank you for your talk, but I have some questions about how the SI's model interact with the land model and the ocean model, because you mentioned that the ice thickness is actually changing within the model. Does that affect the grid cells for the ocean part of the model? And the other question I have is that when the sea ice reach the land model, I mean, the land grid cells, does that have some interactions that will affect if the sea ice can move or not? Thank you.
Right. Excellent questions. So I'll answer the first one, or the second part first. But so in terms of interacting with the land model, we don't have so much interaction there like not direct interaction. We don't have like coastal erosion or anything like that going on because we can't really change the land ocean mask on the fly. However, yes, the internal ice stress term that I talked about causes this sort of drag against the coast. We have a no slip condition there. And so the sea ice can get stuck against the land. And that's just horizontally. Now in CSM3, we're actually going to be bringing in another effect where the sea ice could potentially grow large enough on some of these shallow shelf regions that it could get stuck on the bottom. And that's another way that we have grounded or landfast sea ice that can arise from that process. But that is not in the current model that you're using for this, but will be in a model very soon. The first part is a little more complicated. I mean, we are certainly taking into account the exchanges of heat, fresh water, and salt with the ocean model. But we don't really account for the varying ice thickness in terms of the drag on the ocean. That is just a constant parameterization right now. We hope to, in the near future, develop more of a sophisticated form drag formulation that will take into account the ice roughness underneath, potentially even ocean temperature underneath and things like that. But right now, that ice ocean boundary is generally just when it's freezing and melting, there's these exchanges of heat, salt, fresh water that happen in the thermodynamic part of it, but less so in the dynamic part. So hopefully that answers your questions.
Yeah, thank you. Could I ask one more question?
Yeah,
Sure.
that's fine.
Okay, so I was wondering because those probably limitation for the current model, and we could also show that the current climate model cannot simulate the Antarctica sea ice increase. And I was just wondering, I saw some study that they discussed that might probably because of some feedbacks from tropical SSTs and also the wind speed that affect the mid-latitude in South Hemisphere. And I was also wondering probably that might be another chance that because the land ice glacier, if they melt, they could not be input into the ice model. So yeah, I was just wondering, do you have any idea about the possibility?
Yeah, absolutely. We've done a lot of different experiments where we've played with the wind fields over the continent. We've used these so-called ice ocean data atmosphere forest runs. And even in those, we can't really replicate the trends. And so part of the trend is sort of due to the wind regime over the continent, which, yes, we're not resolving quite as well as maybe we could. But it also may be actually related to a process underneath the ice shelves themselves. There are these pockets of ocean underneath that we don't represent in the model. And so that's an important part because you're not getting this super cold ice shelf water that comes out from underneath of these. And so that could be contributing to part of that bias. But there's been a lot of work over the years that have sort of showed that maybe because of trends in the winds or trends in the southern annular mode or something like that, trends in the ozone, that there's a lot of different possibilities that, again, maybe we're not simulating in the model, but those are some of the sort of missing physics that are ongoing research areas.
Yeah, thank you.
Thanks, Dave. And would you say that the land ice is connected through runoff through the ocean to the sea ice? So there's changes.
Yeah, there is that. But as you know, Peter, we have this snow capping effect, right? And so what happens is that as the snow gets too large on the Antarctic continent, we just start scraping it off and throwing it into the ocean. And then the ocean has to heat it up and melt it. But then what happens in these cold polar waters sometimes is that water is already really cold and you're cooling it down more. So you can actually transfer that sort of solid ice from the continent into sea ice. It's a mechanism. And actually in some areas where it gets stuck, it can just keep that going. it is one of the issues that we'd like to improve on eventually. There's also the question of seasonality. So you think about when snow is accumulating in the winter, and then you're dumping this excess snow into the cold ocean in the middle of winter, when in actuality, we should have icebergs breaking off, and that's the source of fresh water. But yeah.
No, it's always, that's a great area for research for people to think about too.
Yeah, absolutely. Yeah.
Well, I might go to the next question.
Thank you very much for your talk. In one of the last slides you showed, for the Arctic sea ice, CESM2 with Wacom perform better
Yes.
than the with CAM. I'm wondering if you have any insights on that. Is it due to some processes in the higher atmosphere that affects sea ice?
Yeah, really good question. So that paper by Alice Duvivier, which came out in 2021, I think, that actually goes into some of the processes, and it's actually more due to the interactive chemistry that's in Wacom. So the aerosol cloud feedback that's going on in Wacom that's not there in the CAM simulations. And so that has led us to the point of that's really what's causing less incoming shortwave, and hence the sea ice is thicker. But that's still a really interesting area to think about. The other thing we've done, there's a paper by Jennifer Kay that came out just last year or two, where we increased the sea ice albedos just artificially to try to bring it back. And we can actually reproduce the Wacom simulations if we do that, if we just slightly adjust the sea ice albedos too. So there's definitely something we've been thinking about, and there's been a couple publications on that.
Thank you very much.
Great, thanks. So got two more questions.
Oh.
One about Wacom. Thank you.
Oh, sorry, you're done? Oh, same question. Okay.
Dr. Perry, thank you for the talk. It was really nice. I enjoyed it thoroughly. So my question is, first, I just want to talk about that I'm currently trying to compare the sea ice thickness in the Antarctic with the observation, and I'm using the SIMIP6 models. So CESM2 has performed quite well in simulating Antarctic sea ice extent and concentration. That's what the studies have shown us. But when I looked at the thickness aspect, they were not doing that great. And so my first question is that, what do you have to say about the performance of CESM for Antarctic sea ice thickness? And my second question is that even after correcting that equivalent thickness variable, which we had in SIMIP5, would you think how the performance would have changed, or were you likely to correct in future?
Right. That's a good question. I don't really have a good answer for you. I'm not sure what thickness data set you're using for the observations, but you're right that generally we can be biased a little bit in terms of our Southern Hemisphere volume and thickness, but I think that's a much harder thing. We haven't had sufficient observations, at least to this point that I'm aware of, where we've been able to validate that and to really sort of try to get at why. And so it'd be great. I think your work would be really important to help us, to inform us on this. And again, it goes back to the earlier question about just missing processes in the Southern Ocean, I think. So hopefully that is sort of an answer.
Thank you. Yeah.
Thanks, Dave, once more for his talk.